Welcome to lecture 11 of modern construction materials. We have been until now discussing the response of materials to stress. We looked at failure theories, we looked at how materials fracture, and also we looked at the rheological behavior of materials. Now we complete this module of material properties by discussing properties related to thermal behavior. And here to start with, I have a picture of the Tikse monastery in Ladakh. Generally in India, when we talk about thermal behavior, we always think of a very hot climate. We look at how materials will respond to high temperatures and how we have to establish comfort to handle a hot and humid environment. An exception is in Ladakh, which is in the north of India, close to Tibet, and this is a monastery which is very beautiful, very impressive in close to Leh. It is called the Tikse Gompa or Tikse monastery, and you see here at the top the monastery, and at the bottom you see the stupas, and these are all the different buildings comprising the monastery. Okay. So, we will get back to business. We will talk about the thermal properties of different materials. The response of a material to the application of heat is governed by what are called its thermal properties, and there are three critical thermal properties that we are interested in for any material, because they affect the utilization in civil engineering applications. One is the heat capacity, then thermal expansion and thermal conductivity. Now we will look at each one of these in detail and see what are typical properties and compare the properties of the different materials that we have introduced up to now. Heat capacity or specific heat is related to the amount of heat energy required to raise the temperature of a material. Heat capacity is that heat energy required to raise the temperature of a material by 1 degree, that is what is called the heat capacity. So, this indicates the ability of the material to absorb heat from its surroundings, how much heat the material can absorb as its temperature goes up. The specific heat is the heat capacity of a material per unit mass, and its units are given as joules per kilogram Kelvin or calories per gram Kelvin. How this heat is absorbed and stored is of interest to us when we are looking at development of materials and understanding of materials. In most solids, the principal mode of absorption of heat or thermal energy is by the increase in the vibrational energy of the atoms. Normally the atoms would be in a certain lattice position, that say these purple circles denote the normal lattice position of the atoms. When heat is absorbed, these atoms start vibrating and you could have a different position, displaced position, because of these atoms given by the blue dots, which will keep varying due to the vibrations. Another aspect of thermal behavior which is also important to us is the expansion. Most solids will expand when they are heated and contract when cooled. This is generally the case. The change in length with temperature can be given by this equation. Delta L, or the change in length induced by the change in temperature, divided by the original length, gives a thermal strain epsilon Th, which is given as alpha L, which is the linear coefficient of expansion. This is called the linear coefficient of expansion, or sometimes simply coefficient of expansion, times the change in temperature. So, we see that the strain induced by a change in temperature is proportional to the temperature change, and the factor of proportionality is called the coefficient of expansion, and this varies from material to material. Volumetric changes in temperatures can be represented in this form, where delta V is the change in volume due to the temperature increase. The material expands by a certain volume delta V. The ratio between this delta V and the original volume V 0 is equal to alpha V times delta T. Alpha V is the volumetric coefficient of thermal expansion, and this gives now the proportionality between the volumetric strain and the change in temperature, and we find that for an isotropic material alpha V is equal to 3 times alpha L. So, knowing the linear coefficient of thermal expansion, we can find out what is the volumetric coefficient of thermal expansion. Now, why does thermal expansion occur? So, this goes back to our discussion of the Condon-Morse diagram, and we saw that in the valley where the material lattice structure is stable, the minimum value of potential energy or the maximum attractive energy corresponds to a spacing R 0, and this only occurs at 0 Kelvin, the absolute 0 temperature. Above this temperature, that is all normal temperatures, there is a possibility that the spacing can be anything over a certain range. Say instead of the 0 Kelvin, we are at a certain temperature here. At this temperature corresponding to this potential energy or vibrational energy, they can be different atomic positions, interatomic positions, which will have the same energy. So, what the atoms do is vibrate over this energy, vibrate over this range of interatomic spacing, and the average distance would be the mean of this. Say in this case it would be this point R 3 corresponding to the vibrational energy or potential energy E 3. Since this well is not symmetric, it is not symmetric, but it is shaped like this, the mean distance at any energy now deviates to the right. Okay. So, we have a deviation of the mean distances at any energy. So, as the mean now deviates from R 0, the material experiences expansion. This is the expansion that we observe in the material at different temperatures due to the vibration that is occurring in the interatomic distance. So, thermal expansion arises due to the increase in the interatomic spacing as the potential energy increases. And in the well, in the curve between potential energy and interatomic space, the minimum energy corresponds to 0 degrees Kelvin, where the interatomic spacing is R 0. For any other temperature, as the temperature increases, the vibrational energy increases, the potential energy increases, and the average vibrational amplitude corresponds to the well width, that is the range, the two sides of the well at that corresponding energy level. So, the amplitude of the vibration is this. This is called the amplitude of the vibration. The average interatomic distance, that is the midpoint of the well width, increases with temperature since the well is asymmetric, that is what I showed you before. So, as this distance, average distance increases, the material experiences expansion. In the case of metals, the alpha L value or the linear coefficient of expansion normally vary from 5 to 25 times 10 to power minus 6 per degree Celsius. There are some alloys which have much lower coefficients of expansion, say iron nickel, iron cobalt alloys with alpha L values in the order of 1 times 10 to power minus 6 per degree Celsius. Ceramics generally seem to have a slightly lower thermal expansion coefficient. Strongly bonded ceramics have values in the range of 0.5 to 15 times 10 to power minus 6 per degree Celsius. At the lower end we have a material such as fused silica glass, which has a very low atomic density in its packing. The atomic packing density is very low. So, even when the vibration occurs, we do not see any significant increase in the volume. Due to the low atomic packing density, the interatomic expansion produces very little macroscopic dimensional changes, that is, in the material we do not see a lot of dimensional change even though the temperature is increasing. So, we have a low coefficient of expansion. On the other hand, in polymers we generally have high expansion coefficients in the range of 50 to 300 times 10 to power minus 6, sometimes one order higher than what we saw in ceramics and metals, and the highest expansion is seen in linear and branch polymers. If you remember, these are the polymers which have van der Waals bonds between the chains, these are weak bonds, and we do not have covalent bonds between the chains. There we have higher expansion, whereas in cross linked polymers with increasing cross linking, the expansion coefficient decreases, that is, there is less thermal expansion when the cross linking is stronger. And in thermoset network polymers we have the least thermal expansion occurring, that is where you have strong covalent bonds between the different molecules and you have a stiff network structure. Now, when we discuss the Condon-Morse diagram, if you remember, we said that when the bond strength is larger, the melting point is also higher, because the energy needed to break the bond is higher and this increases with the strength of the bond. We also saw that when the Condon-Morse diagram was such that the well was narrower and deeper, that is for a stronger bond, the width of the well being narrower made less variation, gave rise to less variation of the average interatomic spacing at different temperatures, that is, the thermal expansion was also less. So, when we have strong bonds, we have a higher melting point and we also have a lower thermal expansion, and this is what you see here on the curve on the left. We have different metals, and on the x axis we have the melting temperature. So, higher melting temperature indicates a higher bond strength. On the y axis we have the coefficient of thermal expansion, and again a higher bond strength would mean that the coefficient of expansion is lower, and you see a range of materials which fall, range of metals which fall on this line. So, clearly we see that as the melting temperature increases due to the higher bond strength, we have a lower thermal expansion. On the right we have compared 3 metals as a function of temperature. On the x axis we have a range of temperatures going from 0 to about 800 degrees Celsius, and on the y axis we have a percentage change in length. For aluminum and iron we have a linear increase. The coefficient of this is alpha L, that is the coefficient of thermal expansion, the linear coefficient of thermal expansion. We find that aluminum for the same temperature change expands more than iron, and what is interesting is this alloy Invar, which is iron with 36% nickel, which has a final slope that is parallel to that of iron, but initially we see very little or almost 0 thermal expansion until about 100 degrees, and then slowly increasing, and then finally the behavior is parallel to that of iron. But what is interesting to us is this region. We find that over a range of temperature, INVAR does not expand at all, that is the thermal coefficient of expansion is 0 up to a range of say 100 degrees. So, this means that this material will not vary in its dimensions up to a temperature about 100 degrees. That is why we use INVAR as a reference in calibration when we want in the lab to measure change of strains or deformations over a period of time. From one day to the other we can have a different ambient temperature, but we always want to have the same reference. So, in this case calibration is done with reference to an INVAR bar, which we know that over normal temperatures, even though the temperature is changing, will not change its length. So, that is an application of INVAR, and this is one of the few alloys which do not have any significant thermal expansion over a wide range of temperatures. One aspect of interest to us is that there are thermal stresses which can develop due to thermal expansion. Whenever thermal expansion is restrained, there is thermal stress developed. So, you can imagine that we have a bar of steel that is increasing in temperature, it will tend to become longer, but if we had the ends fixed, suppose the bar's ends were fixed and not allowed to move, this thermal expansion now will create a stress in the material because the strain, the free strain is stopped. The material cannot lengthen due to its end restraints, and this resistance to deformation causes a stress in the material. Sometimes this stress is so high that the material breaks or fails, or it can cause failure in the material that is supporting it or fixing it. So, in many cases we have to worry about this thermal stresses that can be built up in a structure, and in some cases also when we combine materials, for example in the case of reinforced concrete, when we are combining steel and concrete, we choose combinations that have the same thermal expansion, so that the restraint or the differential thermal expansion does not give rise to thermal stresses, or we should not induce very high thermal stresses in any structural element that can cause failure. These thermal stresses can also occur due to temperature gradients. Suppose you have the exterior of a body being much cooler or much hotter than the inside, a temperature gradient is set up, and this can also lead to cracking. Thirdly, we can have something called thermal shock, which can also create problems. Suppose we have a brittle material, say glass, that is very rapidly cooled, then you have very rapid contraction of the surface, whereas the inside is still hotter. This creates tension on the surface, because you can imagine the surface is trying to contract, the inside is not allowing it to contract, and the only way that the material can contract is by cracking. So, this creates crack propagation through the material and can even cause failure, and this is called thermal shock. And this is something that might have occurred to you when you have say a glass recipient which was in hot conditions and suddenly you pour cold water into it, the material, the glass can crack. Not something that you should try out, but this is something that could occur, and the phenomena that causes this failure is called thermal shock. Different types of glass react differently to thermal shock. Say when you have common glasses, soda lime glasses with a linear coefficient of expansion in the range of 9 times 10 to the power minus 6 per degree Celsius. This is more susceptible to thermal shock. So, this is a type of glass that I just mentioned. If you have it on the stove heating up, say anything that is being put in it, and then you transfer it to a very cold environment, or you pour ice water into it, then it could crack and break suddenly. On the other hand, we can have glass with lower alpha L values, coefficient of thermal expansion could be lower, like in the case of borosilicate or pyrex glass that is used for heating materials, even for cooking, for in the stoves and so on, we use borosilicate or pyrex glass. This has a coefficient of thermal expansion that is about 1/3 that we see in common glasses. So, this is less susceptible to rapid changes in temperature and less susceptible therefore to thermal shock. So, we saw 3 effects of thermal expansion. One is that thermal stresses could develop when temperature induced expansion is restrained. This thermal stress could cause failure in the material itself or in the surroundings of the material if it is restrained from expansion. Secondly, we saw that gradients could develop, say in a structure you have temperature outside lower than what is inside, you will have contraction on the outside, cracks developing from the outside to the interior. This happens for example in a massive concrete element. Just after setting starts, hydration has just begun, the temperature inside goes up because of the exothermic reaction, whereas the outside in contact with the ambient temperature can encounter cooling, can undergo cooling. This leads to contraction and you have now cracks developing from the outside to the interior, and these cracks could stay in the structure and harm the structure later. So, temperature differences between the exterior and interior can lead to cracking in brittle materials. Thirdly, we looked at the phenomena of thermal shock, where sudden cooling of a brittle material can cause crack propagation and failure. The third thermal property which is of interest to us is thermal conductivity. Thermal conductivity is due to the phenomena by which heat moves from high to low temperature regions through a material. That is, the material transfers heat, and this ability is called thermal conductivity. Thermal conductivity can be defined by this expression, where Q is the heat flux or heat flow. This is equal to minus K, K is the thermal conductivity, it is material property, times the temperature gradient, dt by dx is the rate of change of temperature. The units for Q and K are watts per meter square and watt per meter Kelvin. So, these are the units of K and Q. Now, this heat is conducted by the lattice vibration that we looked at when we look at absorption of heat also. The same mechanism also transports heat through a material. Lattice vibration and the free electrons, say in the case of a metal bond, facilitate the transfer of heat through the solid. So, the heat moves through the solid due to the vibration of the lattice and the free electrons that are present in the lattice structure. Thermal conductivity varies significantly between materials. Say in the case of copper with a conductivity of 401 watt per meter degree Celsius, we can have a case that we have, say, a panel. On one side the temperature is 30 degrees, the other side the temperature is 20 degrees and the thickness is about 1 meter. This would be the rate of thermal conductivity or heat transfer. In the case of silicon, a similar element, silicon has a much lower thermal conductivity, we see that the heat passes less. Most of our civil engineering applications, say in buildings, we want lower thermal conductivity in our walls and the shell and the envelope that makes up a building, because we do not want to be influenced too much by the temperature changes outside a building or the structure that we live in. So, we want something that insulates, which behaves in a manner closer to silicon rather than in copper, with less heat coming in the case where you have a very hot climate outside, or less heat going out if you have a very cold temperature outside. This rate of heat conduction depends on the conductivity of the material, and this influences the thermal comfort in the area that we are living in or working in. There are a range of thermal conductivities for materials. So, this is at room temperature, and on the y axis we have the value of K, and you see a range of values. At the bottom are materials like gases, which are good insulators, and solids, which are good insulators, like fibrous materials which have a lot of air pockets and voids in them. Foams, polyurethane foam is a very good insulator that is often used in the filling of walls, so that heat does not go through. Then come the metals, then in other solids we have lower thermal conductivity in non-metallic solids, and in metals and very pure crystals we have higher thermal conductivity. These are good conductors, whereas these are good insulators. What are the ranges of thermal conductivities? In metals we have a range of 20 to 400 watt per meter Kelvin. We also see that as the composition of the material changes, the thermal conductivity changes. On the right hand side we have this graph showing a copper zinc alloy, composition varying as shown in the x axis, and the thermal conductivity varying with the composition like this. So, we find that as more zinc is introduced into the copper, the thermal conductivity drops, that is the lattice has less possibility of transferring the heat as more impurities in the form of zinc are put in. Generally we find that alloying metals with impurities tends to decrease the thermal conductivity, as we see in this case in the copper zinc alloy and also in stainless steel. In polymers, the thermal conductivities are in the order of 0.3 watt per meter Kelvin, and here the heat transfer is realized by again the vibration of the molecules and the rotation of the chain molecules. You remember in polymers we said that the polymer chains have a high degree of rotation, movement without the chains being broken, and this ability to rotate and vibrate facilitates the heat transfer. A polymer with higher degree of crystallinity, that is a more ordered structure, more arranged structure, will have higher conductivity than an equivalent amorphous material which has a lot of space between the chains. In the case of higher degree of crystallinity, we have a better packing, and therefore the conductivity is better. Many polymers are also good thermal insulators, again because of the amorphous nature and the lack of packing. In ceramics, we find that thermal conductivity has a wide range, say in the range of 2 to 50 watt per meter Kelvin. Glasses and some amorphous ceramics have lower conductivity than crystalline ceramics, again as the packing increases, conductivity becomes better. The porosity also influences the conductivity significantly. since the thermal conductivity of gases is very low, like the thermal conductivity of air is only about 0.02 watt per meter Kelvin, and in the pores of these ceramics we have air which is not facilitating the conductivity. Thermal conductivity of ceramics also decreases or can decrease as the temperature increases, at least at lower temperatures, due to the scattering of the lattice vibrations. At higher temperatures, conductivity may increase due to radiant heat transfer. Instead of conductivity, the conductivity through lattice vibration, heat could be transferred by radiation. So, here you see how thermal conductivity changes in some materials as a function of the temperature. You can see in the case of a dense stabilized zirconia, you have an increase in the thermal conductivity as the temperature increases. In other cases you have a drop and then the effect of radiation coming in, and there is an increase in the thermal conductivity. This is a table from Callister showing you the 3 properties that we have discussed: specific heat, coefficient of linear expansion, and thermal conductivity. In the first column we have the different values of specific heat, the second column we have the coefficient of thermal expansion, and in the third column we have thermal conductivity. This is the group of metals, then we have ceramics like glass and alumina and so on, and then we have polymers. We find that the specific heat of metals ranges from about 100 to about 1000 joules per kilogram Kelvin. Ceramics are slightly in the higher end of the same range, going from about 700 to 1050 joules per kilogram Kelvin. Polymers much higher, almost double the values that we see in the ceramics and aluminum or more. So, more heat is absorbed for a unit change in temperature. Coefficient of thermal expansion, again we see a wide range, with metals having values in the range of 5 to about 25 times 10 to the power of -6 per degree Celsius. Ceramics ranging from 0.5 to about 15, and polymers having much higher values, more expansion in most of the polymers. Thermal conductivity, we see obviously that metals are much better thermal conductors, whereas we see polymers are poor conductors and probably good insulators. Ceramics have a variation. You have glass with very low thermal conductivity, whereas something like beryllia which has a very high thermal conductivity. So, these are the different properties, and I have explained to you how we use them or how they affect us in civil engineering applications. So, to conclude, we have looked at the thermal properties that are important to us in civil engineering applications of different materials, and this concludes this module on properties. We have looked at mechanical properties, we have looked at rheological properties, and now we have looked at thermal properties. We went to properties after looking at the microstructure, how the material develops, and we looked at range of structures that form in materials on the basis of the bonds that form in the molecular scale, and then that led on for us to understand why materials behave in a certain way when stress is applied and when temperature is applied. Now, after this we will go on to look at individual materials, and we will try to review these properties as we go through these materials, and we look at where the different materials are used and in what applications. Thank you.